talks have been by veteran, by senior people, and this talk, as we had Shangomitra also a couple of weeks before also, and Stuart also, they are very young, but that doesn't mean they are young in terms of work. They have done very significant work, and I know Stuart pretty well because of association with Dr. Iyer, who is a very close friend of mine. So I know their group do very high quality work, and also not only Professor Ayer's supervisor, Professor Ayers also. So they have contributed immensely in this particular area of metamaterials. And as you know that there are two different aspects and two different concepts of metamaterials. One is the resonant particle approach, another is the transmission line approach. So I believe Stuart is going to have a very nice session on the transmission line approach applications, because I'm aware of some of their work. We have done some work with Justin also, who was a senior student, probably graduated, I believe, in 2017 or so. So one of my PhD student and Justin, with a supervision from Iyer and myself, did a very good work, which was published in Journal of Applied Physics, and few more are in pipeline. Also, Shango was associated in another work where we did some dielectric resonator based and for bandwidth reconfigurable. So we are really happy to collaborate with the group of University of Alberta, Stuart, Shangomitra, and of course Ashina. We are really thankful to and acknowledged to. So coming back to this particular initiative, and as I already mentioned, that this is not just a standalone initiative, this is being continued, and I have huge support from my office bearers, especially Professor Anum, Mr. Arijit Mitra from Vikram Sarabhai Space Center, ISRO, and these students. They are the real pillars of the chapters. The entity chapter and APS and entities GEC Barton Hill student branch is jointly hosting this particular event. And just to mention, especially to Stuart and others, that this chapter has also taken an initiative to organize an event which is named as L4. There are 4 L: learn from leaders and learn from legends. L, 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 L. So those talks have also been very successful. And these kind of talks by young people like Shangomitra, Stuart, and on some other days we had some other young speakers. These are, more close to the young students because they are really working in their hands, so they can actually tell you a lot of aspects from more practical scenario because they are working in hands. So their talk will be more appreciated. Especially it will be more accepted by youngsters, the young students, especially the UG and PG students, because I know that a large number of enthusiastic students who want to shape their career in this particular area of antenna propagation, micro theory, and techniques. So I don't want to take much time. Once again, thanking the speaker, Mr. Stuart. He's going to be Dr. Stuart very soon. And also sincere thanks to the office bearers and student members. I extend the virtual podium to Aishwarya. Thank you very much again. Thank you.
Great. Well, Dr. Saha for the kind introduction. Thank you, Sivat, as well.
Yeah. So now it's my pleasure to introduce the speaker. Even though I said already that he's going to submit his thesis pretty soon, but let me introduce him formally. Stuart Barth received the BSc and MSc degrees in electrical engineering in 2012 and 2015 respectively from University of Alberta, Edmonton, Canada, where he is currently working towards the PhD degree under the supervision of Dr. Ashina. His current research interests include the study of multiconductor transmission line metamaterials, fundamental electromagnetic theory, passive Barth circuit design, and antenna radiation pattern shaping. Mr. Barth received the IEEE APS Pre-Doctoral Research Award in 2014 and IEEE APS Doctoral Research Grant in 2016 for his ongoing research into electromagnetic bandgap structures for antenna and waveguide applications. He serves as an officer of IEEE Northern Canada section and its MTTS and APS joint chapters. So just for the sake of audience, I can tell these two awards of PPS doctoral research and PPS doctoral research award. This is highly prestigious, highly competitive. So that Stuart has received this award says a lot, and this is a very glorious beginning of his career. And I believe he is going to, be another stalwart like Ashina. Thank you very much. Over to you, Stuart.
Thank you again for the kind words. Thank you everyone for attending my talk. So this is my presentation on multi-conductor transmission line theory and its applications to modern metamaterials. Again, this is thanks to you, the IEEE MTTS Kerala chapter and IEEE MTTS and APS student branch chapter of GC Barton Hill. So today I will be going over a quick introduction to where I work at the University of Alberta, where I am a PhD candidate. I work in the Microwave and Meta Devices Laboratory under the supervision of Professor Ashwin K. Iyer. In this laboratory, we have access to several state-of-the-art equipment, notably some fabrication equipment. Our LPKF mechanical and laser milling machines enable us to create state-of-the-art components for our research. We also have on the measurement side an NSI 6-axis near-field scanner inside of a ETS Lindgren shielded anechoic chamber for which to do antenna measurements, and we connect with a Keysight Technologies PNA up to 40 gigahertz. On the inspection side, we are capable of doing our own PCB work. We have a digital microscope with 100 times 16 megapixel, just to be able to really do some fine and very delicate rework on our PCBs when needed. So we are very privileged to have all these sophisticated equipment to be able to produce, design, and validate these metamaterials in-house. And we'll see some of that later on in the presentation. So the outline of this presentation is as follows. I'm going to start with a brief look at transmission line theory, in particular its history and some fundamental properties of transmission line modes. Then I'll be going into multi-conductor transmission line theory, how we define multi-conductor transmission lines, the various methods that we use to describe propagating modes in these systems, notably what we call the terminal domain and the modal domain, and then looking at transformations between these two, which is a change of basis and why that is important. From there, I'll be going into the theory of multi-conductor transmission line-based metamaterials. So a quick history of development of the metamaterials and how we define these frequency-dependent block modes that we see inside of these structures. And then a key property of these metamaterials is that there is modal coupling, which creates all sorts of interesting dispersion properties, such as band gaps. Then I'll be going over some specific applications and future directions of this work, in particular parallel plate mode suppression and multiband antennas using band gap structures, miniaturized or dual band filters and couplers using microstrip-based metamaterials. And lastly, just quickly looking at multi-dimensional metamaterials and computing block modal properties and some of the issues that we have going on there, which I am solving as part of my PhD research. So to start with, transmission line theory actually began through a large contribution by a man named Oliver Heavyside, who did his work primarily at the end of the 19th century. And Heavyside worked as a telegraph operator, the Danish Great Northern Telegraph Company. And he was an operator that actually used and saw firsthand this newly laid telegraph cable from Newcastle in England over to Denmark, as I've indicated with the pink line here. And as an operator, he noted several technical limitations on this cable. For example, the large amount of required power and voltage necessary to send signals through the cable, as well as things like signal distortion of the telegraph signals. And he was a well-read individual, so he actually read Maxwell's newly published work on the propagation of electromagnetic waves. And over the course of a number of years, He derived similar equations to Maxwell describing the propagation of electromagnetic waves, but he cast them in terms of voltages and currents inside of a two-conductor, one-dimensional system. And these today are what we call the telegraphers' equations in his honor. And as you can see in the modern form of telegraphers' equations that we have top, they're actually very, very similar in form to his original equations here that you can see at the bottom. So really not much has changed, some minor notation, but his work was pivotal in establishing what we use today. Now, transmission line theory on its own is a very powerful tool in helping us to describe transverse electromagnetic modes supported between two conductors. And what this means is that the fields are orientated in such a way that they are entirely contained in a plane transverse to the direction of the propagation of the wave, right? And what this allows us to do, we know from vector calculus, is that we can take these electric and magnetic fields and integrate them in these transverse planes to produce unique scalar voltages and currents, right? And this is an important concept. Because when we have these voltages and currents instead of fields, we can start combining them in interesting ways. So of course, you know that we can take these telegraphers' equations and combine them to create wave propagation equations, as you would see in the top right. And of course, we know we can take general solutions to these differential equations, which describe the wave propagation behavior. And from this, we can derive quantities such as propagation constants in the bottom left and characteristic impedance on the bottom right. But what this actually allows us to do is create some very interesting applications, right? So for example, canonical microstrip circuits. So these are devices whose physical sizes are on the same order of magnitude as the wavelengths they respond to, right? In these devices, phase is a critical parameter, but it's also easily controllable, right? So we are able to create some very interesting phenomena by just simply adjusting phase. And of course, this allows for the integration of electrical propagation effects into the domain of classical circuit theory. So this allows us to take discrete lumped components and combine them with distributed effects. And this means that critically, we can model things like time delay, pulse dispersion, input impedance, etc., in the circuit domain, which would not be possible without this transmission line theory that converts fields, E and H, right, electric and magnetic fields, into circuit quantities, voltages, and currents. So now multiconductor transmission line theory extends the concepts of transmission line theory to systems of more than two parallel coupled conductors. In general, in multiconductor transmission line theory, we assume that there's coupling between all of the conductors. And this allows us to write a set of linear equations, as you might see here on the right-hand side. Some history of this, it's actually quite interesting. Once again, Oliver Heavyside, in a 1880 work, actually investigated multiconductor transmission line theory. So as you can see in the figure in the top left, he wrote out these sets of linear equations and investigated the various behaviors of the charges and voltages in this system. Later on, Louis Pipes in the bottom left, he worked on really bringing these concepts to use the modern matrix notation that we use today. So he wrote the telegrapher's equations as matrix equations. And shortly after, Stephen Rice was really involved with just solidifying the notation that we use today in terms of impedances and coupled values and things like that you find in modern notation. So physically, we want to represent quantities in these multiconductor transmission lines intuitively as voltages and currents on each conductor, right? That is, we express them on a per conductor basis. So the voltages are typically expressed, which we typically number as 0, right? And the currents on all the conductors sum to 0. That's a requirement of transmission line modes. So in this way, we can describe the currents and voltages on each conductor with respect to the reference, which is always assumed to be carrying the balance of currents. Now, if we take the propagation and telegraphers equation, we can express them in matrix notation, right? So for example, those sets of coupled linear differential equations I showed previously can be summarized in these forms shown in the top equations in terms of propagating voltages and currents. These, of course, once again, can be combined, as we do with regular transmission line theory, into wave equations involving the matrices of per unit length, admittance, and impedances. From here, what we can do is we can define things like the per unit length, admittance, and impedance as consisting of per unit length quantities like resistance, inductance, capacitance, inductance. This is pretty standard undergraduate material, but cast into matrix notation. And that's just due to the coupling between all the different conductors. But this form raises several questions, right? How do we describe a wave in this system? What is a wave's propagation constant or characteristic impedance or other properties? What if we have an inhomogeneous system, such that the transverse cross-section contains multiple different materials which support differing wave velocities? How does that affect a wave that's propagating down this MTL? Well, there is an analytical basis for answering this question. And physically, it comes from the fact that we can represent independent waves traveling along these conductors. And the core idea to that is that the essence of a single wave is corporate propagation, which means that all of the currents and voltages of a given wave propagate at the same speed. So in the figure here, I've drawn the phase difference of these fields. And you can see that all the voltages and currents corresponding to these fields should have the same phase in order for this corporate propagation to occur along the transmission line length. Mathematically, we describe these using the equations I've shown. We simply have the voltages and the currents, and they're modulated along the length by the propagation constant of that wave. Right? Now, from here, it would be even more convenient to express these fields as a single wave, right? These equations here detail vectors of voltages and currents. That do we have multiple voltages and multiple currents involved, right? So could we represent these with a single voltage and current corresponding to a wave? So we call these voltages and current distribution modes. Right? So similar how a two-conductor system supports one transmission line mode, one TEM mode, these multi-conductor transmission lines support multiple such modes. So we're interested in how to determine the properties of these modes. And in order to do this, we define two forms of representations, or what we call domains. And these domains are equally valid representations of our multi-conductor transmission line system. So for example, the terminal domain details the voltages and currents of each conductor, as we've described previously. This is, again, is with respect to an established reference, and we use the subscript T to detail the terminal domain information. So in this terminal domain, various quantities such as per unit length capacitances describe coupling between all of the conductors. So mathematically, we would express this property as a fully populated matrix, as you can see in the bottom left corner. Right now, in the modal domain, we have a different scenario. Here, the voltages and currents are described on the basis of each mode. So we have sets of voltages and currents, which we describe with, which we attribute the subscript M, right? But notably, various quantities corresponding to these modes are decoupled from each other because we are interested in describing independent waves. So mathematically, we represent these as diagonal matrices. And the mode can actually be described by propagation in independent two-conductor transmission lines. So One two-conductor transmission line system describes the propagation of one mode, as we understand from basic transmission line theory. Now, there is a formal relationship between domains that we've essentially already described, right? So if we take the equations on the left, this tells us about the voltages and current waves on each conductor, right? And on the right, we have the matrix representation of the differential equation describing the propagation of waves in our MTL system. So what we do is we combine these two equations, as shown in the bottom middle, and what we find is that we get an Eigen system. And why is this important? Because we can then go and we can solve this Eigen system for all of the appropriate eigenmodes and eigenvectors. So if we do that, we actually get the equation shown on the top right here, where the matrix uppercase gamma squared m is the diagonal matrix of the squares of the modal domain propagation constant, right? Where each entry is the square of a valid modal propagation constant gamma, right? Again, this is a diagonal matrix being a modal domain matrix, and this implies no coupling between the modes, right? So it's describing independent waves. The eigenvectors in this system tell us the voltages and the currents, how they are distributed for each mode. So TV is the matrix vectors of the voltage propagation equation, and Ti is the matrix of eigenvectors for the current propagation equation. What we can do is we can take this expanded equation and substitute it back into our original wave equation, as shown in the top left. And what we get is this interesting system shown in the top right. Now, I've underlined these key properties that we have, which are the terminal domain voltages and currents multiplied by the inverse of the eigenvector system. So what we actually do from here is we take these quantities, and as shown in the middle left, we define new quantities, which are the modal domain voltages and currents, right? So what this equation tells us is that we have a specified relationship between the modal domain and terminal domain currents and voltages, which are essentially completely described by these eigenvector matrices TV and TI. And we note that if we go perform this substitution, what we get is a set of wave equations in the modal domain. So what we've done now is we've transformed the basis of our system from the basis of terminal domain voltages and currents into the basis of propagating modal domain voltages and currents. Right? So as shown in the bottom middle, these are the exact equations we use to change bases between modal and terminal domain. And the change of basis is a very mathematical concept, as you know, but it's very valid here. And as I'll show going forward, the fact that we know it's a change of basis allows us to make some inferences about the physical quantities of the mode. Interestingly enough, this terminal to modal domain conversion process is not a new development. Once again, Oliver Heavyside was on the case in the 1880s, and I've highlighted some text from his work. He says, so that we may represent the actual potentials of the lines, that is the terminal domain quantities, as linear functions of the potentials of an equal number of imaginary lines having no influence, that is the modal domain. So now that we understand all the math and the physics behind it, how can we use it? Well, this is where the applications to metamaterials comes in. So as you may know, metamaterials are artificial composites which support bulk behaviors not found in naturally occurring materials. And of course, there are a rich variety of dispersion features and numerous applications that have been investigated over the years. And I've shown sort of the canonical metamaterial here, which is the split ring resonator wire media. And we know that we can design this type of structure to get a number of interesting things, such as this dispersion diagram shown on the right, which shows backwards propagation and bandgap and other sorts of interesting phenomena. But interestingly enough, metamaterials itself has a history that comes out of something that goes even further back in history, which is artificial media. And there are several key players and key concepts in artificial media that help guide the development of metamaterials. So one key player was Winston Koch in the left, who investigated these metallic lenses that he made for steering electromagnetic radiation. So while most lenses of his were made from dielectric, he showed that he could make the same type of lenses from sheets of metal plates. Walter Rotman in the middle investigated artificial plasmas made from periodic arrays of thin wire elements. And he showed that when electric fields impinged on this thin wire media with the right polarization, it experienced a bandgap behavior similar to what you might expect in a plasma. Lastly, one of the key people here was Gabriel Krohn, and Krohn showed that he could model the effects of wave propagation in different media using equivalent circuit models. And this is a key development in transmission line metamaterials because we essentially employ the same concepts to model the effects of propagation through various metamaterial media with similar transmission line models. So transmission line metamaterials actually came from a subset of artificial media, which is artificial transmission lines. Once again, Oliver Heavyside was one of the first investigators in this field. He proposed that signal distortion could be minimized along the length of a telegraph cable by periodically loading it with series inductors to minimize signal distortion. And of course, we know that there's a condition which is now called the Heavyside condition, which I've shown in the equation here on the left, which basically tells us how to get a very low dispersion system. And because he couldn't affect the properties of his transmission line as he wanted to, he proposed creating this artificial transmission line through periodic loading. And that was way ahead of his time. Later on, Michael Pupin in the United States used series inductors and shunt capacitors to emulate the phase effects of very long transmission lines in short lines that he could investigate in his laboratory. And of course, transmission line metamaterials use a similar concept. So these are periodically loaded transmission lines, which exhibit phenomena not found in conventional metamaterials. Sorry, found in conventional metamaterials, not found in conventional materials. Series capacitors and shunt inductors are typically used in 1 or 2 dimensions to periodically load transmission line systems or grids. And the benefits of transmission line metamaterials is that they are simply modeled and rigorously analyzed. And the ideas and the fabrications are scalable from DC all the way up to infrared frequencies, right? Wherever transmission line theory is valid. So some key work in this field was actually completed in part by my supervisor, Ashwin Iyer, and he investigated 1-dimensional and 2-dimensional transmission line metamaterials, a key feature of which is this so-called backwards or left-handed propagation. This is something that's found only in metamaterials, and in these propagation modes, phase and group velocities are contradirected. And this is an important concept that we'll use later on, but it's sufficient to note that you can't find this behavior in natural materials. Sorry, all right, continuing on. Multiconductor transmission line metamaterials really extend this work. And so the idea is we periodically load multiconductor transmission lines, and these exhibit material behaviors such as left-handed modes, but additionally, they have a host of other interesting dispersion features, such as band gaps. So I've shown here an example of one of the first multi-conductor transmission line metamaterials by a researcher at the University of Toronto by the name of Francis Alec. And he investigated the bandgap behaviors of a MTL metamaterial. But he also showed that he could rigorously model the system with multi-conductor transmission line theory. Notably, right, he showed that you had to load conductors of the multi-conductor transmission line system with reactive circuit elements, right? But this is in the terminal domain. But what we want to understand about these metamaterials is the effects and the properties of waves propagating through them, right? So, and by waves, we mean we're interested in the mode of the system. So we want to know the modal domain properties of this metamaterials. So this shows how the terminal to modal domain transformations I talked about earlier are essential to understanding this process, right? Or being able to analyze this process. So the modes supported by an infinitely periodically loaded MTL are called block modes. And these in general assume a homogenization of a metamaterials unit cell. And what we do is we take the equivalent circuit model in a typical analysis, and we concatenate it down into a ABCD matrix, right? That just describes the propagation of voltages and currents through a two-port network. Then we take a circuit form of Bloch's theorem, shown in the bottom left. And all this does, again, is specify that we're looking at a single mode, right? We are looking at voltages and currents which propagate through the network with a given phase, right? And all the voltages and all the currents have the same phase, right? So this is one mode. And we combine this with our ABCD matrix to get another Eigen system, right? So it can be shown that if we solve this Eigen system, we get the block modes of the system. But interestingly, the block modes, due to the frequency-dependent nature of the loading reactive elements, capacitors, inductors, etc., the block modes are also frequency-dependent. So this means we can have interesting effects happening, such as modes overlapping on a dispersion diagram. So I've shown some examples in the bottom. So on the bottom left, we have an example of a right-handed mode, shown by the red curve, overlapping with a left-handed backward mode, shown by the blue curve. And this is something you don't see in traditional regular two-conductor transmission line metamaterials. As well, we get other effects, such as the overlapping of two right-handed or forward modes. Now, the interesting part about this overlap is that when the modes have similar fields, they will actually start to couple with one another in regions where they're phase matched, or we say overlap on the dispersion diagram. So we understand through previous work that there's an exchange of energy that occurs between these modes as predicted by coupled mode theory. And one of the unique phenomena we see in multi-conductor transmission line metamaterials is that contra-directed group velocities between two modes can cause the formation of band gaps. And moreover, these band gaps are predictable with the MTL-based modal analysis that we understand. And this isn't really new behavior. This modal coupling was exampled many years ago. So for example, in the top right, I've shown some of the work of Pierce, who worked in depth with coupled mode theory. And he showed that the exchange of energy between forward or backward directed modes resulted in these various types of band gap. But as a more standard description of a problem, I've shown some figures in the bottom left where if we take the curves in the previous slides and we allow these modes to couple, we get some very interesting dispersion properties. So for example, we get a band gap shown in the bottom left figure, where the right-handed forward mode couples with the left-handed backward mode, such that there's a complete exchange of power between the two modes in the band gap region, and there's no net flow of energy. And this is what we call our band gap. because energy cannot propagate in this region for these modes. As well, with the forward-forward mode, there's an exchange of energy that occurs. And if we look at the resulting coupled system given by the black curve, we see that these modes have now been altered so they don't exist at the same dispersion angles and frequencies as they did before. So we can do some dispersion engineering with this type of behavior. Lastly, I'd like to note with respect to band gaps in particular, unlike traditional optical or semiconductor band gaps that you might see, the existence of mode at a given frequency does not mean that there is a complete net zero flow of energy at that frequency, because we understand from a microwave modal perspective that other modes can exist inside of band gap regions. So this means that dissimilar modes may exhibit completely unrelated behaviors. And I'll give you an example of that shown with the data below. So on the left-hand side here, we have a dispersion diagram showing various modes. The exact system doesn't matter in this case, but if we look at the scattering properties of the various modes, as I've shown in the other four columns, we see some peculiar behavior. If we look at this second column here, we see that there's a band gap between roughly 0.5 and 1.3 gigahertz. But then if we hop over to this third mode here in the fourth column, we find that in this region, there's strong transmission. In fact, there's no suppression of this mode, but there is suppression of this mode at a higher frequency, right, between about 1.2 and 2 gigahertz. And this last mode here, shown in the rightmost column, never even sees a band gap. The energy just propagates straight through, unimpeded. Right? So this allows us to really have a modally dependent behavior out of our metamaterials, and in particular, utilizing band gaps to suppress certain modes, not just net energy, as you might see in the optical domain. So this is where really understanding the properties of this comes in handy. And I'll go through some applications of this. So one of the first multi-conductor transmission line metamaterials developed was parallel plate mode suppression via shielded Stephen-Piper structure that I've shown in the bottom left-hand corner. So we know that the classical Stephen-Piper mushroom structure supports a left-handed or backwards wave type mode, whereas an upper shielded region above the Stephen-Piper surface supports a right-handed or forward parallel plate type mode. And in this work of Dr. Alex, he showed that the coupling of these modes produced a stop band or band gap region. And indeed, he saw a large amount of scattering suppression, so a very high insertion loss through the structure in the frequencies he predicted, as shown on the plot on the bottom right. And of course, he showed that he could well model this with multi-conductor transmission line theory. Some more work that's actually work of my own and Dr. Ayers that extended this concept was parallel plate mode suppression without the use of vias. So we showed that the coupling of a left-handed coplanar waveguide mode with a right-handed parallel plate type mode would also produce a band gap. So this coplanar waveguide-like mode is shown here on the left with the parallel plate-like mode, and you see that there are various degrees of field similarities. That means these modes will couple. So when we load this transmission line, as shown in the middle plots here, this is looking top view of the structure. When we load this coplanar waveguide with series capacitors, as shown by the blue surfaces, and shunt inductors, as shown by the red surfaces, and corresponding to the equivalent circuit shown here, we actually get a band gap region, as indicated by the green highlighted region in the right-hand figure. And we showed that we could actually create this structure in a fully printed manner, as shown in the bottom middle figure. And this means it's very advantageous for PCB type environments. So what we showed for this is that we could contain fields inside of a single-layered metamaterial-based bandgap ring. So what we did was we took this EBG, metamaterial electromagnetic bandgap structure, and we folded it into a circle. And we looked at the transmission of signals between a via inside of the circle and a via outside of the circle. I've shown a view of that here in the top left, and beside it, a cross-sectional view where the metamaterial exists on a single copper layer inside of this multi-layer PCB environment. And the structure is shown on the bottom right-hand side, which has dispersive properties shown in this dispersion diagram here. There are a couple of things to note. Firstly, the equivalent circuit model agrees very well with the HFSS data given by the black dots. And as well, inside of our bandgap region, we actually have another mode propagated. But we know that because this mode is not related to the parallel plate mode that we're interested in, it won't have an effect on the suppression of power, right? So understanding this, we can go ahead and we can create this metamaterial EBG structure. And we showed that outside of the bandgap frequencies, around 4 gigahertz, the fields are not contained anywhere inside of the structure. They just propagate freely from one via to the other. However, at frequencies inside of the bandgap range, for example, at 8 gigahertz, we see strong confinement of fields inside of this metamaterial bandgap ring. And this is because the mode is prevented from propagating through this EBG structure, so the power has nowhere to go but resonate inside of this ring. This idea was continued and developed to enable the development of dual band microstrip patch antennas. And the idea here is that we could affect similar cavity resonance at 2 independent frequencies. So what we did was we took a traditional microstrip patch antenna and we integrated these metamaterial bandgap structures to the 2 radiating slots of the patch. And what we showed is that the fields could be sufficiently suppressed such that at one frequency of interest, for example, at 5 gigahertz, the resonant mode would be supported over a short frequency range. But outside of this bandgap frequency, the fields would very easily propagate through the metamaterial such that the length of the effective length of the cavity was increased. And now it resonated at a lower frequency at 2.4 gigahertz. And you can see in this dispersion diagram, just verification, sorry, of the dispersive properties of the unit cell, where we have propagation at 2.4 gigahertz and a bandgap region at 5 gigahertz. This was also used to affect dual band patch antenna in a circular form for use in GPS antennas. And again, you can see that at one frequency, the fields pass through the metamaterial bandgap layer. But at a second frequency, shown on the right, the fields are contained inside of this metamaterial ring, such that the cavity mode resonates at a different controllable frequency. Other applications of this work include miniaturized couplers, enabled using the complex modes found inside of these bandgap regions. So for example, in the work of Dr. Islam, also from the University of Toronto, he showed that if we had 2 adjacent microstrip-based metamaterials, one supporting a left-handed backward mode and one supporting a right-handed forward mode, again, they would couple, form a bandgap region, which had these complex modes in them. But the nature of the complex modes could be tailored such that a certain amount of power couple between the block modes. And he used this to design a coupler to extract a certain amount of power out of the mode. So he could create a 3 dB coupler, a 10 dB coupler, or whatever level he wanted, which could be predicted analytically through this multi-conductor transmission line analysis. And as well, the coupler was miniaturized because the use of the reactive circuit elements, inductors and capacitors, would create a shorter electrical length of the microstrip type mode. This work has also been extended to create uniplanar metamaterials that are embedded directly into the microstrip sections of various devices. So for example, I've shown here a metamaterial-based electromagnetic bandgap structure embedded directly into a microstrip section. And we use the phase properties of this metamaterial to affect dual band operation of the coupler. So if you look at this dispersion diagram shown on the left-hand side, I've shown that at two frequencies, labeled F1 and F2, the same dispersion angle or phase is supported by the block mode that propagates through this structure. So if we excite a microstrip mode on this line, we see that it occurs the same phase at two different but controllable frequencies. And this allows us to make things like this quadrature hybrid coupler, which exhibits fairly similar performance at two controllable frequency bands. So for example, here we designed it for GPS frequencies, GPS L1 and L2. Also developed are uniplanar metamaterials for use in networks which support multiple branches. This was done by my colleague, Braden Smith, and he showed that he could use the bandgap properties of microstrip lines embedded metamaterials to affect a sort of routing process, a frequency-dependent routing. So he showed that at one controllable frequency, he could cause the microstrip mode to propagate through this dashed line, this short dashed line that I'm highlighting, and it would not propagate through a longer section, even by this longer dashed line. And that was just by tuning the various properties of the bandgap structures. And then at a second frequency, the reverse would take place. So this bandgap structure would prevent the propagation of signals through it, while the other metamaterial bandgap structure would allow propagation through this longer curve. And in this way, dual band phasing would also be achieved because this outer path has a physically longer length. And so he could design the structure to obtain the desired performance at, again, two different bands. So he showed that he could make this Wilkinson power divider operate at 2.4 and 5 gigahertz with desired properties at both frequencies. Another one of my colleagues showed that we could use this technology to implement uniplanar microstrip filters. So we showed that we could create a very, very small bandgap in terms of frequency through some design of this metamaterial bandgap structure. And so as shown on the dispersion diagram on the left, there's a very narrow bandgap range supported, and he showed that he could use this to create a very narrow band but controllable filter. So as shown on the right, the filter has a very well-defined stop band region, but also this was created, again, simply by embedding the metamaterial into a host microstrip line. So really, it's just a microstrip with some copper sections removed. So fabrication-wise, right, these are all very simple devices, but they take up no additional space, which is a strong advantage if you're looking at very space-constrained environments. So you can imagine there's a lot of future work that might come out of these developments. So what we're working on from here, is achieving more elaborate behaviors for things like wave guiding, beam forming, or imaging, which requires a very in-depth analysis method, similar to the work that I've shown here. So some ideas from this are the analysis of multi-dimensional or multi-port network shown on the left. Beside it, I've shown this Rotman lens. right, which are very electrically large structures for signal routing applications. But this could be imbued with a metamaterial and miniaturized a significant amount if we knew how to properly control the waves propagating through the structure. Another avenue of investigation that's been examined recently is the development of fully 3D or 3D printed structures for the development of metamaterial lenses or beamforming surfaces. And lastly, of course, meta surfaces are a very hot topic right now. And this still deals with the properties of waves propagating through periodic structures, right? So you can appreciate that even if we're looking at a meta surface where a wave propagates through one layer of a surface, we're still interested in knowing how we can affect an exchange of energy such that we can manipulate the properties of the structure to affect things like beam forming and imaging. Some of my own work that's still under development involves determining the properties of multiconductor transmission line modes. So interestingly enough, this is an unsolved problem in multiconductor transmission line theory. We know from linear algebra that eigenvectors may be arbitrarily scaled, right? So we have these matrices, TV and TI, which I spoke about before, which affect our change of bases between the modal and terminal domains. But these are actually key matrices in computing things like per unit length impedance and admittance of these modes, or characteristic impedance of these modes. And at present, it's understood that these modal values may not be uniquely defined. And as you can imagine, that's a problem if we want to know the properties of these waves propagating through our metamaterials. So there are many future developments in this field. I'm excited to see what we can do with all these forms of dispersion analysis and interesting applications that can come out of that. So thank you for your attention very much. I can take your questions now.
Good morning, sir. Good morning. This is good morning, Stuart, sir. This is Anu Mohammed from Barth Engineering College. So it was a very interesting talk, sir, and we could learn so many things from the talk. Sir, my basic question is could you elaborate the distinction between model domain analysis and terminal domain analysis? Could you please?
Could I elaborate on the analysis of the two modal domain and terminal domain?
Yes, sir. Could you please?
For sure. So once again, the terminal domain describes the voltages and currents, right? So when we're looking at properties of the terminal domain, we're talking about properties of coupled systems. So we know that these voltages and currents will produce fields, electric and magnetic fields around the conductors, which will cause mutual coupling between those various conductors, right? This is where we get things like the mutual capacitance between the conductors in these large matrices, right? Now, in the modal domain, we're looking at the properties of independent waves, right? So each wave can be described with a single voltage and a single current. And this means that there's no coupling involved. So by the way we've defined it, when we're looking at properties, there aren't any mutually induced properties between different modes. They're all independent of each other. And this is what allows us to have these matrices that are diagonal, right? As in there's no effects between different modes. And these modes, again, are individual waves that are propagating through our metamaterial structures, right? As opposed to things like the terminal domain voltage and current, in which case we could have sort of distribution of voltages and currents, right? Which may not form a coherent wave that's passing through our system.
Sir, that means you want to say that in the multi-conductor domain itself, that means the terminal domain itself, segregate the various modes, and then we will be doing the analysis in it, sir. Model domain. Hello, sir.
Sorry, could you repeat the question?
Sir, that means you want to, in essence, you want to say that in the multi-conductor terminal itself, if we can segregate the various modes and we can do the model lines, model analysis, and separate the various modes, isn't it, sir?
Yes, that's right. Yeah, that's the goal of modal analysis, to look at the properties of these independent waves.
Sir, Raghavan sir is there from NIT Trichy. Sir, Raghavan sir, if you are there, sir, please, please, can you unmute and can you ask the question, sir? Raghavan sir. Okay, sir, there is a question from one of the professors. Can you read the question, sir? Stuart, but sir, are you there?
Yes.
Sir, here some question is there. Any work is going on FSS with metamaterials by you?
By myself?
Yes.
Yes. So let me return to the presentation. There we go. So some of these works that I showed lastly are my own. So for example, this work with parallel plate mode suppression without vias was a work of my master's thesis. These works on antennas I did in collaboration with a colleague of mine, Aigen Smith. And this work on dual band couplers and power dividers and filters was also done in collaboration with Aigen Smith and Jacob Brown. And some of my future work, again, does involve the analysis of these multidimensional networks and solving this problem of determining the properties of all of the block modes for things like per unit length, admittance impedance, and characteristic impedance, which in the current understanding can't actually be done. So I'd love to comment on this, but I haven't published any of that material yet. So it is under development, but forthcoming very soon.
Thank you, sir. Thank you. Sir, there is one more question from another participant. He is asking, can you elaborate bandgap region in the dispersion diagram? What's the advantage of two different frequencies having the same phase?
What's the advantages of two frequencies having the same phase? So you're probably referring to this plot here on the left. So in and around a bandgap region, right, we have this sort of curving of the mode, right? And this allows us, again, to have two frequencies that I've labeled here, F1 and F2, which have the same phase, right? So now if we're thinking about a structure like a canonical coupler, right, which requires a phase length of 90 degrees to operate, right, on each of these branches, right? That means that traditionally, we just have one frequency or harmonics of that frequency, which have that 90-degree phase, right? But using this dispersion engineering, we're actually able to create two frequencies that have these 90-degree phases really at any frequency that we want. So now we're not just limited to one frequency and its harmonics. We're able to have one frequency and then a second frequency that we also choose. So we have effectively dual band behavior of this structure at any two bands as well.
Sir, so far no other questions have seen in the chat box. Sir, this multi-conductor transmission lines based metamaterials, up to what frequencies did you work, sir? What was the highest frequency you worked?
Well, that's a good question. I mean, I myself have only worked with it to X band, but of course, all of this theoretical analysis and everything I've done hinges on the core concepts of transmission line theory, right? Which really, at its core, deal with the propagation of voltages and currents. So to answer your question, I would pose another question, which is, in what frequency range can we define voltages and currents, right? And of course, as you know, this hinges on things like the TM approximation, where we assume that the fields of the modes are predominantly existent in the transverse plane, right? Transverse to the direction of propagation. So this becomes increasingly incorrect as losses of the system increase, right? Like ohmic losses of the metals. So generally, it's considered that the theory is only valid up to past infrared frequencies, right? So you wouldn't really be able to use these modes at optical frequencies. Metals are just too lossy, right? But essentially anywhere below there, wherever transmission line theory can be validly applied, any of these concepts can be applied.
Okay, sir. Okay. Then there's another question whether you can implement the MTL based metamaterials in UWB MIMO antenna systems.
Yeah, for sure. I mean, again, it's we haven't really looked at many wideband applications of these multiconductor transmission line modes, but of course, it can exist, right? We see from these dispersion diagrams, let me get to one here, that we can have a rich variety of effects, right? So, for example, in this structure, we see a canonical band gap region in this frequency range. But of course, we have other things like modal coupling between these two modes here, and that's affecting a certain behavior. So depending on what kind of behavior you want to see, the chances are you can affect that type of dispersion behaviors with multi-conductor transmission line mode. And of course, if you're in specific applications of antennas, I encourage you to check out these previous works by our group.
Okay, sir. Thank you very much, sir. If any other questions are there, if Stuart sir, if you are if they can directly communicate, can you share your email ID so that if any participants is having any doubt, can you share your email ID?
Yes, for sure. It's I may not have had it on the first here. It's sbarth@ualberta.ca. You can find me on LinkedIn or ResearchGate or any of those, and I'd be happy to take questions there.
Thank you very much, sir. Thank you very much, sir. And or back to Shivada, you can continue with the proceedings.
Yes, sir. Sir, I request all of you to turn on your video so that we can have a virtual photo shoot. Thank you, sir. It's done. So now I invite Srimati Bhupika to deliver the vote of thanks. Bhupika ma'am.
Shivdas, maybe some net connectivity or some issues madam will be facing. So if you could please carry on with it.
Yes, sir.
So you please deliver the vote of thanks, Shivada.
So it's my pleasure on behalf of MDTS Kerala chapter and IEEE APS and MDTS student branch chapters of Government Engineering College, Barton Hill. It's my pleasure to deliver the vote of thanks. So I thank Engineer Stuart Barth sir, who has been the speaker of the day, and he delivered an excellent lecture on such a wonderful topic, which of relevance the current research scenario. I take this opportunity to thank Sri Ajit Mitra, Sri Dr. Chinmay Saha sir, and Professor Anu Mohammed sir, who have been the three pillars of IEEE MTTS Kerala chapter and have been the guiding beacon to all of us. Once again, I thank all the participants for uh, showing their patience and attending these lectures. Hope to see you all in future lectures as well. Thank you.
Shivada, just check whether Chinmay sir is there.
Sir, are you there?
I am there. I won't take much time. I think Stuart should have a proper breakfast now, right? So, yeah, it was a wonderful talk as I expected. Thank you very much, Stuart. Keep it up, and all the best for your PhD defense soon. And visit India sometime. Maybe you know that we organize some focused AP conferences and MTTS conferences here. INCAP, Indian Conference on Antennas and Propagation. I guess Ashin has attended twice. We started Indian Antenna Week, in 2010, and till 2017 we have organized this Antenna Week in a very holistic fashion. We have MTTS focused event also, IMARC, which happens every year in India. This year it was supposed to be IIT Kanpur. Anyway, due to this pandemic, we couldn't do next year. Again, it is scheduled in IIT Kanpur. So I invite you to visit India during some of our conferences, and then you can definitely visit us in Kerala. It's a nice city, beautiful beaches here. So we'll be very happy to host you sometime here. Thank you. That's it.
Sounds good. Thank you. Great. Well, thank you.
Shango Mitra is there? Shango, are you there?
Yes, I'm here. Yeah, I'm here.
Are you in a proper configuration to turn on your video?
Kind of. Yep.
Yeah. So you may have a valedictory talk or something like that, a felicitation talk for a minute or so.
Like, I've known Stuart for almost 7 years now, and I recommended his name because I felt like he's an excellent speaker. So, as you have all seen now, that he can deliver a great talk, and I'm glad that I did that. So, yeah, that's about it.
Good. Yeah. Incidentally, Shango is moving to US for his postdoc. So all the best to Stuart as well as Shango for their future endeavor, academic endeavors and other endeavors also. Okay.
Thanks.
Yeah.
Okay.
Shiva, Let's conclude the session.
Yes, sir.
If Orijit is there, Orijit.
That's all that I guess.
Okay. Yeah.
So thank you all for attending. Hope to meet you all in the future sessions as well. Thank you. So may I close the session now?
Yeah.
Yes, sir. Thank you.